Good morning, and once again, welcome to my YouTube channel, Pearson and Excel International Maths by Mr. Kamotho. And we continue to explain Pearson and Excel International A-Level Math, Pure Maths, Book 3. And in this video, I want us to continue explaining chapter number 7. And this is integration, a very critical and important chapter in Pure Mathematics 3. And I want us to just go straight to example 8 on page 153. And we want to understand what is the reverse chain rule. Remember, we saw the chain rule in differentiation in the previous topic. And all this is explained in my videos in my YouTube channel. But there's a way we can use the reverse of chain rule to integrate some specific functions. And we are told that if a function can be written in the form, the function can be written in the form kf prime x, that is the derivative of the function of x, you can integrate it using the reverse of the chain rule. What do we mean by reverse of the chain rule? Reverse is assuming a function that must have been integrated to give us what we already have. For example, let's just be specific. To integrate expressions of this form, try ln fx, and differentiate it to check and then adjust any constant I would want to just be very practical in this. If you have a function whereby the numerator looks like or appears to be a derivative of the denominator, then the reverse chain rule now here comes in handy, because we are going to assume a function which is going to be ln fx, and differentiate this to verify whether it's going to give us this derivative, and if there are any constants, we shall adjust the constant. And I just want to go straight to example 8. And explain what's happening there. Example 8 on page 153, we are told to find the integral of 2x all over x squared plus 1 with respect to x. Now, who cannot see that the numerator, which is 2x, is a derivative of the denominator, which is x squared? We all know that. Forget about the constants, they will put themselves into their places. So let's talk about, because now the numerator is a derivative of the denominator, we say let's talk about why we must talk about the natural logarithm of fx, which is at the denominator. Y is equals to ln x squared plus 1. And at that point, we differentiate the natural logarithm of the function of x, which is ln x, dy dx to be equals to, of course, we know anytime we are differentiating ln x, it becomes 1 over x rather. So the differential of this becomes 1 over x squared plus 1, of course, times the chain rule now here comes to play, because we must differentiate the aspect of x, or rather we must differentiate that particular term that is containing x. Yes, we have differentiated the whole expression, but the chain rule cannot be complete if we do not differentiate the inner core, or the core term, or the factor that is containing the x, so times 2x. That is the differential. So the differential is 2x all over x squared plus 1. And this confirms that this is what we were integrating. So whatever we suggested as our function to differentiate, to take us here, has worked perfectly. Therefore, the integral of 2x over x squared plus 1 is simply natural logarithm of x squared plus 1. Natural logarithm of x squared plus 1. Of course, plus a constant c. And why are we saying this? The integral of this is this. Remember, we realized that it's in the form of a derivative over the function, and therefore we, as the law has it, we suggested that we must try differentiating natural logarithm of fx, and that is what we have. Y is equals to ln x plus 1. Of course, differentiating this, confirm whether it will use this, then we have realized this perfectly, giving us what we had. And therefore, if this is a derivative of something, we realize that if we integrate a derivative, it takes us back to the function. And therefore, the integral of a differential will always take us back to the function. And that is exactly what we have. But of course, the c has to come in because we do not have we don't have limits. We don't have limits in our integral. All right.